let me first point out one thing about the textbooks that you're going to receive. So I've made edits in the textbooks compared to the version that you have. So you have the February 2020 version. So with some feedback from this summer's camp and feedback from interacting with you, I've done some additional things like labeling diagrams. So some of this, like I had talked about doing or thought about doing, but I hadn't fully implemented. So your versions of the books, or the version of the book that will arrive for the students, will have these points labeled, and it'll talk about the importance of labeling things. In an earlier chapter, so chapter 5, there's actually boxes for, where did it go? So there's actually boxes for the kids to plug in or write what column they've plugged things in. And it's color coded so that they know that different colors mean that these need to be in different column or different half board columns for the circuit to work. And similarly, like a more complicated circuit like this, every single one of these nodes has a box associated with it. So you know that, okay, all 4 of these components need to be plugged into the same red box. These 3 components that meet here need to plug into this purple box. And whatever number I put in, I plug in my first element to on the board and I write it here. I know I need to plug in these other 2 components into that same box. So hopefully that will help with building these circuits. Okay, so let me switch back to this one. Nope, wrong one. Yeah, so we want to work with this. Okay, so continuing the labeling. So we saw that we plugged in the microphone, and hopefully you can see, I'm having fun like switching between these different screens and trying to keep track of what's visible. Okay, so we have the microphone between 4E and 5E. We have the red wire of the battery on the red rail and the black wire of the battery on the ground rail. So what I've done so far is I've plugged in, this is now connected to the red rail, and I've connected the other side of this to the blue rail. So what's missing is in the circuit, I need to have a jumper wire between 4E and my blue rail. So I'll do that, or the part of the board connected to column 4 on the lower half. So I'm going to take my blue wire, or not my blue wire, my green wire, and go between 4A and the blue rail. So that's this connection here. So with that plugged in, I've made from 4E to the blue rail. So that's this connection. It looks like I'm 1 column off, but it doesn't matter because this rail is all connected. And then on this side, I need to connect my resistor to the red rail. So I'm going to take the resistor and I'm going to go from 5E. Oh, okay. So this is where jumper wires help. So one of the things that I notice is, okay, so I want to connect from 5 at the bottom up until the red rail. But when I do that, if I were to just plug this in like that, I'm going to have a problem where this resistor is going to touch the metal of the microphone and it's going to short circuit. So instead, what I've done in terms of my preferred solution, I put a jumper wire between 5 at the bottom. So I go from 5B, I went to 3H. That's so that I'm able to work with my resistor and not have it in the middle of the rest of my circuit. So now I can plug in my 22 kilo ohm resistor. So essentially what I've done is I've made 5E. This is a common point with 3H. So I can do either 5E or 3H. That's equivalent. That's this equivalent point on the circuit. So now I can do my 22 kilo ohm resistor between oh, it looks like I went into 2, sorry. I have a solution. So I have two versions of this circuit side by side, so that I can build it in terms of things that work out well. So I have 5E and 2H. That's my point number 2. And then now I go from there to the red rail. So I go from here. And because I know that I'm not going to use this part of the board, I push my resistor out of the way so that I can plug other things in. So I have the resistor in the leftmost red rail and also in column 2 at the top. And then finally, my capacitor is going to go from this common point, this 2, into some other column. So in this particular example, I just made it go to the next column. So this is 2, 2, 3. That's the value of the capacitor. And I just have it moving over by 1. Hopefully everyone can see that. Okay, so now we're ready to measure. So question? Yes.
Yeah, quick question for you. Sorry, now I can't see your talk for a second because we got to see your screen again.
You're looking for my face?
There you go. No, no.
No.
No. But you had to talk in order for us to get back to your Elmo camera.
Oh, all right. Strange.
So that is, so I had done it the hard way, stretched it around and bent it so that it wouldn't touch the side of the microphone.
That's fine.
Showing that learning had occurred. And so now with that 22 in F, you have that going between which 2 rows?
Oh,
rows
so I didn't label the next part. So for number 3, I have this connected to row 3. So this is actually in 3J. So the left side of this, so the capacitor, so I encourage you not to label like the J versus the H versus the E. It's better to just keep track of it. Is it the upper half or is it the lower half? So the capacitor is just on column 3 in the upper half of the board. And the other end of the capacitor is in column 2 in the upper half. It turns out that it's in J rather than in H, because H is where I have my jumper wire going.
Yep. Helpful, thank you.
You're welcome. So can everyone see this? Can see the board clearly? Okay, any other questions? Because we're going to jump into measurement, and the measurement is going to be challenging and fun. I don't quite know how this is going to work out, so we're going to try something and see how it comes out. So the next step is you need your digital multimeter, okay? And you're going to have your connections to red and black. So we're measuring voltage. So the right side is red, the middle is black. And we're going to tune to AC voltage. So we're slide it over 2 because that's what we want to measure. We want to measure how much the strength of the alternating part of the signal is rather than the offset. One trick that I found in order to do this measurement more simply is that we're going to measure everything relative to this position G and D. So I don't think you're seeing the screen. Maybe you're not. Yeah, probably not. You're not seeing the PowerPoint, correct?
We're seeing your diagram.
You're seeing the diagram, not the overhead.
Correct.
Huh, okay. So how do you know, well, I guess how do I control, oh, so do I have to stop?
We're currently seeing your diagram, and we're also seeing your breadboard.
Oh, okay, all right, so perfect. Okay, so you're just not seeing my face. All right, so that's what I'm aiming for. Okay, so the trick that I found, because what we want to do is we want to measure the voltage between 2 and ground, between 1 and ground, and between 3 and ground. So ground is connected to the battery, and so the trick that you can do, you can look at the battery clip very closely. On one side, the side that's connected to the black wire, and then the other side is connected to the red wire. What we're going to do is we're going to insert our probe inside the spring of the battery clip and then plug in a battery into the spring. And you can't have the probe go too far down into the, you just have to play with it until it goes in. So what this allows me to do is it saves one hand in terms of where I'm touching on the circuit. So I have the probe inside the spring, and now it's able to have my measurement relative to that point in the circuit. And then I plug in the other battery. Okay, so I have my battery and my battery clip, and I have, hope everything can fit. I'm balancing something on top of a piece of paper on top of a piece of cardboard. This is quite interesting. Okay, so I want to measure voltages at different parts of the circuit. I'm realizing I do need an additional hand, so let me see if I can get all this to balance. Okay, so what we want to do is we want to play a tune into the microphone. And unfortunately, the ability to generate a tone onto your microphone, you need some form of sound generation device. You could sing if you wanted to. It's not going to be a constant volume sound, so it's going to make the measurement more difficult. So what I have is I have this iPhone app called Tone Gen. I'm just going to play this as a demonstration. For your part, you can probably just talk or sing and just see what's going on. So I'm going to turn up the volume. It's going to play this annoying 705 hertz sound towards my microphone. Hopefully I can balance everything. All right, so everyone should be annoyed that they hear the sound. And what we want to do is we want to measure the voltages at specific locations. So let me pause this because there's another thing that I need to do, which is I've created a document, shared document, where we can record, go this one. Okay, so we can record our results together in the shared document. So it's a Google spreadsheet. Not sure why the chat's not showing up. Okay, so do that. Screen. Okay, so the idea is that we want to make measurements at different parts of the circuit, and then we're going to record the voltages that we've measured. So there's a section for measuring the AC voltage. There's a section for measuring the DC voltage. So we're going to focus on the AC voltage. So the circuit that we have, oops, so we want to measure position 1, 2, and 3. So the first one we're going to measure is 1. So does anyone have a guess as to what voltage I should measure at position 1 if I'm measuring AC voltage? And any guess for what I should measure if I'm measuring DC voltage? So I'm measuring from here to ground. Oh, and people are responding in chat. Okay, so Kenny says 3 volts. So yeah, so 3 volts will be the DC part. The AC part should be 0. So let me play the sound. Okay, and so now I want to measure at position 1, which is this location on the resistor. And I can see that I have 0 volts AC. If I switch to DC, I get 3.18 volts. So based on that measurement, I would go into the spreadsheet, and the AC voltage is 0. The DC voltage at position 1 is 3 volts, so 3,000 volts. Okay, so now I'm able to go to position number 2. So position number 2 is at the microphone. So I need to measure either 5E or 2H in terms of my connections. So looking at the circuit, it's actually easiest to probe the resistor's other end. So I need to plug in the probe at the resistor's other end. And so I can see the DC voltage is 0.01, or sorry, the AC voltage is 0.015. The DC voltage is 0.236. So this was 236 millivolts. and this is 15 millivolts. And you may or may not have this annoying sound available to your microphone, but maybe if you're listening, it may play through. Okay, so now I'm ready to measure at point 3. Point 3 is the opposite side of the capacitor. So in DC, um, okay, so DC I get 185, and AC I get the same 15 millivolts. So 185 for DC and 15 millivolts for AC. Okay. Yeah, that's quite an annoying sound. The reason that I'm doing this is because I need a constant amplitude signal going into my microphone. I mean, singing can also work, but it's a lot of moving parts and a lot of things to hold on. Okay, so questions on this first part. Hopefully your ears are not ringing too much. Okay, so this 15 millivolts that we have, so remember this is us singing or playing this really, really loud note. 15 millivolts is very, very weak. I'm not going to be able to transmit and radiate this as an electromagnetic wave with such low power. So what I need to do is I need to amplify the circuit. And so it looks like I have two versions of PowerPoint with slightly different things. So the second activity that we want to do is, okay, this is the part that we've built so far. We've built the microphone, this first resistor, and this capacitor. And we said, okay, we have 3 volts from here to here. There's a certain amount of current that flows through this device. And the microphone, what it's doing is it's changing the amount of voltage that drops across of it. And so the change in voltage on the AC part is like 15 millivolts. And therefore the current, or sort of the voltage that's going across this resistor is changing. So there's a current that's flowing through this resistor that's varying in time. And then this capacitor is blocking most of the DC part. We saw in the experiment, it's actually not doing that great of a job of blocking the DC part, but we have an AC signal of 15 millivolts. We now need to amplify this very weak signal into something that we can transmit. So we need something that has a large amplitude to it. So to do that amplification, we're going to use a transistor. So the transistor amplifies current. So there's a certain amount of current that's going to flow from the base through the emitter. And because this transistor is operating in amplification mode, that's going to amplify the current that's flowing through the collector emitter. And so what that's going to do is it means that at this location, because you have these 2 resistors, you're going to end up with an oscillating signal where the amplitude is bigger than what you came in with. So what we want to do now is we want to build this part of the circuit. So we want to add the 1 mega ohm resistor, the 10 kilo ohm resistor, the transistor, and the 100 nanofarad capacitor. So let me switch back to this. So in this diagram, to be able to add 1, 2, 3, 4 components, remember we're not doing the speaker. So to add those 4 components, so we're getting rid of this. To add these 4 components, we need to introduce 2 new nodes. So this node, which was originally just open by itself, now we need to connect the transistor, and then this node needs to connect to a capacitor. Now, I'm going to show you how to do the transistor because the choice that you make and how you wire this can make things significantly easier if you do a specific choice for where you put your transistor. So I'm going to pick where I put my transistor, and I'm going to use, so keep in mind the transistor has a flat end and it has a rounded end. So with the flat end facing us, the left column or the left element is the collector, the middle is the base, and the right is the emitter. So the left edge is this top part in the diagram, the middle is the base, and the right edge is the emitter. I'm going to pick to plug this in such that this is in, the left edge is in, so with the flat side facing me, so the flat side is facing the column A or the row A, I'm going to plug this in such that the collector is in 9B, the base, which is the middle, is in 10B, and the emitter is in 11B. So what I've done in terms of my choice, so we still have these in this diagram. So 4E is here. Oops. The blue rail is still here. 5E and 2H is still there. The red rail is still connected here, and it's also connected here. So what I've done in my choice with how I've positioned the transistor, my collector, it's the left edge. This is in 9B. My base, I've picked to be in 10B, and my emitter, I've put in 11B. So with the transistor in place, now I need to do, oops, I'm missing one number. So for the other end of the capacitor, this happened to be in, oh, it's already there, just in the wrong spot. Okay, this other end of the capacitor was in 3J. So I need to connect my capacitor to the base. So I need a jumper wire from here to here. I need to put in this resistor, this 1 mega ohm resistor. One end is on 9, the other end is on either 3 or 10. This one end is going to be on 9, the other end is going to be on the rail. This one, I need a jumper from the emitter to the rail. And then this capacitor needs to go from 9 to some other part on the board. So we'll give you 10 minutes or maybe 12 minutes. Yeah, 12 minutes. So at 2:30, well, let's do 10 minutes. At 2:35, we'll come back and we'll discuss the solutions. And feel free to ask questions as you're going along.
Linford, does it matter which end of the resistor you place down? Like, if I
No,
were to,
the resistor is interchangeable in its direction. It's
and
only, oh, go ahead.
oh, so the capacitor is the one that you have to pay attention to which end you're placing down?
Some types of capacitors you do, these ones you don't. So this capacitor is interchangeable in its direction. The only things in terms of your STEM clubs that the polarity matters are the microphone and the light emitting diode. And if there's any diodes or transistors, those are the ones that the direction matters.
Okay, thank you.
Mm-hmm.
Langford, I hate to ask you to do this, but could you do me a favor? And the last thing you did was you went through and you pointed out the areas that we need to be thinking about what needs to be connected where. Can you run through that one more time for me?
Sure. So what we've built in the first half was we built this part of the circuit. So this part in here is already taken care of, and this edge is already taken care of, right? We did that as the first part. So what needs to connect is we have these two new resistors, the transistor and the capacitor. So we have 4 components we need to plug into the boards, and we need to make electrical connections to the various pins within those parts. So we plugged in the transistor in 9, 10, and 11. And so you can see this one is in 11, but I need to make a connection to this rail. And then this one is in 10, but I need to make a connection to the capacitor. So I need a jumper wire from here to here. I'll need a jumper wire from 11 to the rail. And then up on the top, I can see that, okay, I have a 1 mega ohm between here and here. So I need to have this resistor go either from 3 to 9, because this is on 9, or I need it to go from 10 to 9. So it's up to me which one I pick. And then for this component, I need to go from the rail to this node. So this is all node 4. So although the dot is here, it's equivalent to this dot. So this is all connected currently to 9. So I need to have a 10 kilo ohm go from the red to 9B. So, and the other thing is you have to keep track of, are you working on the upper half of the board or the lower half of the board? So the transistor is on the lower half. So because it's on the lower half, I need this resistor, this 10 kilo ohm, to go from the red rail into something on the lower half of column 9. I see Scott has figured out how to do a top view. I have a low cost solution, which is so I have two webcams, and one webcam is clipped to my lamp and it's just above sitting on a cardboard box. And then I have this other solution where I do my cell phone recordings where I have a stack of books and the cell phone is perched in between the books. And that gives a stable variable distance to the um, to the thing I'm trying to record.
I think I may be done. I'm not sure.
Oh, who is this one?
Dr. Coleman.
Okay. Do you want to share your circuit via the screen?
I'll try. Am I able to share yet?
Oh, so I need to stop share. Okay, go ahead and try again.
I was going to try to tilt mine. I don't know if this is going to work or not. Oh, I just try to hold it up.
Oh, and if you leave your multimeter on too long, it starts beeping at you.
So I don't know how clear this is.
Okay.
But,
There we go. Resistor, capacitor. I think, so this is the first half of the circuit or the second half also?
well, I have the
So you have
resistor, the capacitor, I have the emitter.
Mhm. So I think, so let me share screen. So I think what you've built so far, let me minimize, too many windows open. So you have this part of the circuit and you have this part. I didn't see the 1 mega ohm and the 10 kilo ohm and the second capacitor yet.
Or I haven't had that.
So those three parts. Yeah. So my thing is beeping at me. So if you leave your digital multimeter on for, I guess, more than 5 minutes, it goes into auto shutdown mode. Okay, so let's rejoin. So I'll walk people through as we continue to build. So some people may be finished, but make sure that we make these connections. So we have a connection between the emitter and the blue rail. So I'm going to go from 11A to the blue rail with one of these jumpers. So I've made this connection from 11A to the blue rail. So now the emitter is connected. So now I need to go from this part. So I need to connect from the capacitor to the base of the transistor. So I need a jumper wire because the capacitor is all the way over here and the base is over there. So I'm going to pick, I just have an orange wire. So I'll go from here to the base. So that's the jumper wire. Oops. Trying to get things visible. Okay, so I went from the capacitor to the base. So that's this connection. So I went from column 3 in the upper half to column 10 in the lower half. So that made this connection between the capacitor and the base. I now need to have this resistor. So the resistor actually goes between the base and the collector. So I can go between columns 9 and 10 on the lower half. So I have my 1 mega ohm resistor, and it's going to be bent very tightly. So I'm going in adjacent columns. So one is going in 9 and the other is going 10 on the lower half. So all right, so I plug those two in. So one end is on 10 in the lower half, the other end is on 9 in the lower half. So I've made this connection in. So now I want to put the 10 kilo ohm between 10 and the red rail. So this 10 kilo ohm resistor, I'm going to go between 10, which is the base. So let me move this. All right, so not the neatest, but it's effective. So I have one end in the red rail and the other end is in 10. This one happens to be in 10C. So I've plugged in this resistor now. So the new thing in my labeling is that, so these two are actually the same. So basically node 4 is 9. So actually I don't need this new label, but essentially this node is, this whole thing, all 4 of these components are connected to 9 on the lower half. And then the last thing I need to add is this capacitor from here to an open row, or sorry, an open column. So I'm going to go from, wow, looks like I'm out of space. It looks like I'm going to go from 10A, and then it seems like it's going to land in 14A. So I made this position 5 be 15. Oops. And now that I look at this diagram, I realize that I plugged it into the wrong end. So this capacitor should be in 9 rather than in 10. So let me fix that. So it should go from 9 to, well, now it's reaching 14 instead of 15. So I went from 9 on the left-hand side of the capacitor to 14 on the right-hand side of the capacitor. And I should have said this while I was doing this. I realized I did not do this. And so lesson learned, Anytime you're modifying your circuit, you always want to unplug it. So unfortunately, I did a worse practice, which is to adjust my circuit while it's plugged in. And it's obvious that if I do something incorrect and I short circuit while this is plugged in, it's going to damage the circuit and it could possibly burn something. So always unplug the circuit. You can unplug just one end of the circuit and that breaks the circuit. So assuming that I did that first initially, correct, where I unplug the circuit. At this point, I would now plug back in my circuit. And then I would go to measure voltages. So we get to be revisited by the lovely music of the tone generator. And so I'm going to play the signal again. I remember where I had it. So my measurements may not be consistent because I'm doing this non-sequentially. Let me just double check. So after the capacitor, last time for AC, we had 15 millivolts. This time we have, oh, I had it here before. Okay. So this time we now have, looks like 0. And just check. Okay, so I'm getting 0, and I'm wondering whether it's because I've connected additional elements to the circuit or if I've damaged something. I'm worried that I have damaged something. Okay, so for the AC voltages, it looks like I'm getting 0 everywhere. Well, here's 9. 0. Okay, so I'm going to switch to my backup circuit. So I suspect that as I connected elements with things still plugged in, I may have damaged something. So here's my backup circuit. The functionality is, functionality is unchanged. Okay, so let me play this again. I'm going to record AC voltages again. So on the capacitor, I have 9 millivolts, or 6, depending on which side I'm on. Okay, so instead of 15 millivolts, I have 6. And now what I want to do is I want to measure. So at this point here, I measured 9. Here I measured 6 millivolts. And now I want to measure 0.4. So at 0.4, I would connect, and I can make contact anywhere in column 9. And you can see that the AC voltage is huge. It's 490 millivolts. And then, what's this? So for 0.4, I had 490 millivolts. So it significantly boosted the strength of the signal. So here, this was actually 9, and this is 6, because I'm now working with my backup circuit. So the values are slightly different. That's not as critical. And then I want to measure 0.5. So at 0.5, I need a capacitor, and it looks like in my backup circuit, I hadn't put in the capacitor just yet. So the capacitor should go from column 9 to some random other column. Okay, so I'm going to go from 9 to 14. So let me play this again. So on column 9, it was 450 or so millivolts. And then after the capacitor, I still have 450 millivolts. The DC part, on one end, the DC is 1.09 volts. and the other end it's 152 millivolts. Okay, so in terms of my recordings, this was 109 millivolts. Oops. Or sorry, this was 1.09 volts, and this was like 150 something millivolts. And then on this one, it was 490 and 490 roughly. So that's how I go about measuring the voltages on the circuit. And so what we've seen, and the biggest takeaway from today, is we now understand the functionality of this part of the circuit. We have our power supply, and what we're doing is we're using the microphone to convert sound into an electrical signal. This resistor is allowing us to vary the voltage at this point. The capacitor takes the signal, which has our voice, and it's going to remove most of the DC part or most of the offset. So the amplitude is the same. It's just I've subtracted and centered this around 0 rather than centering this around some non-zero offset. And then this part of the circuit is an amplifier. So what I'm doing is I'm taking this signal and I'm using the transistor to amplify the voltage that is a result of current flowing from the base to the emitter. This signal is now large enough, so it's 0.5 volts out of my 3 volt power supply. It's now large enough that I can then send it and remove the DC part. So you'll notice that the DC part over here dropped from like 1 full volt to 158 millivolts. So it subtracted off most of the DC part of the field. So at this PowerPoint, nope, this one. So at this point, I now have a signal that I can then radiate as my FM transmitter. So what we've built today is this part of the circuit. We've built the microphone, the resistor, the capacitor, the first transistor, and we understand we're converting audio into electrical, we're amplifying it, and then we're filtering it so now it's suitable to be radiated away. And typically in STEM Club, we would just build this and we would put this part together on the soldered breadboard. So we would solder together all of these components. Your students are going to put together this part of the circuit using the breadboard. So in the same way that you labeled each one of these nodes, you're now going to label these nodes as well. So what it will look like is we've posted to Box this worksheet. And so you've built this part of the circuit. You've labeled these points. So you're up to point number 5 in our circuit. So we've built this part. So what you need to do as your assignment, your asynchronous part, is to build what's in this blue dotted box. And we're going to use the same principles as before. For each one of these nodes, so these particular nodes are measurement nodes. There's one node that's not labeled, but you should have a dot here as well. So for each one of these nodes, you should write out what column you've plugged things into so you can keep track. And again, when you plug in this transistor, be careful with how you lay it out. So I've plugged it in and I've looked at the orientation and I've picked, for example, 9, 10, and 11. You need to pick 3 additional columns for this transistor. The last interesting element is the antenna. So the antenna is just a piece of wire. So I don't have, well, I guess I have it now. Okay, so you have this wire and it's roughly 40 inches in length. What you'll need to do to be able to use it, because the end is not stripped, you have to take scissors and you have to carefully remove the insulation from one end of the wire. So you're going to essentially take, I'll have a pair of scissors nearby. Oh, here they are. Okay, so technique for stripping wires with scissors. So what we're going to do is you're going to have your scissors, and instead of cutting all the way through, you just gently rotate the wire or the scissors around, and you just keep doing this until you stripped off and made a cut in the plastic. And then you pull. I'm a little bit out of practice and it's kind of hard to do on the video, but so you strip this around a little bit, you rotate the wire around, and then that cuts the plastic. And if you have sharp nails, you can then pull the plastic off. Wow, out of practice. Okay, So you can twist this back and forth a few times, and looks like I need to do a little bit more cutting with the scissors. All right, it looks like I'm not going to get it right now. Being on the spot trying to get something to work, it's always fun. Okay, so another trick is, and this is not fully recommended, so the backside is the side that's getting stuck. So I should cut the backside a little bit more. There we go. All right. I don't have long nails today. All right, so I finally pulled this off. Okay, so I've now removed the insulation, and then you can twist the remaining pair of copper. And then this is going to be what plugs into your proto board. And so you find the appropriate column. It may turn out that not all of the wire will fit in, so just twist this a bunch of times. It helps to cut this twisted end. It makes it sharper. Just have a place for where these crumbs are going to go. And then after the cut, this should be able to plug into your proto board at the location of where your antenna is going to go. And if it doesn't plug in easily, you can remove some of the pairs in this twisted wire. So that's going to be how you plug in the antenna here. All right, so questions. So let me stop screen share. Does it make sense what you're going to do for your asynchronous learning? Yes, no?
What's the tiny screwdriver for? I'm guessing
Oh,
it's for
the tiny screwdriver, yes. So once you've built the, let me switch back videos. So once you've built the, I'm realizing we're also going into the debrief time. So once you've built the final circuit, so let me move some stuff out of the way. Your final circuit is going to look like this, but just on the breadboard. The tiny screwdriver is to tune the FM station. So once you've built everything and you've plugged it in, there's a testing procedure, and Aditi is going to record the video on how to do the testing. Essentially, you're going to have this set up. You're going to have the wire, the antenna straight up from vertical, so it's going to be taped to something. And then you need an FM receiver, such as your car radio, or maybe you have a home radio. You're going to tune to, let's say, FM 100.1. And that's going to be a part of the radio where it's very staticky. And then you're going to play music or whatever into your microphone. And you're going to very, very gently tune the capacitor, this yellow trim cap, which is a tunable capacitor. And that's going to adjust the frequency that this circuit oscillates at. And so the turning that you're going to do, it's going to be like 5 or 10 degrees in terms of your steps. So you want to make very, very small steps in your tuning of the capacitor. And so we have these really tiny screwdrivers to do that.